So let's take a look again at our topographic features that we care about here in the Sunda Subduction Zone, Sunda Trench, the Nicobar Fan, the 90 East Ridge, and the Bengal Fan. So again, sediment for the last 30 or million years ago or so has been coming down into the northern Indian Ocean. Part of it splits off and goes to the west, which we won't discuss any further today. What we care about is the part that heads off to the east, gets funneled in that direction by the 90 East Ridge, down into the Nicobar Fan, and then because of subduction of many high ridges, most of the sediment that comes further than that is getting funneled down the actual trench axis. So let's take a quick look first at the eastern part of the system. So we're going to concentrate on the area around Java. So in this area, the Indian Ocean has a number of seamounts, lots of rough topography out here, hardly any sediment on the trench itself, mostly oceanic pelagics. There's a bit of sediment that makes it all the way down the trench axis, all the way down to the end, but not very much. So it has a deep trench that's funneling that sediment. Again, remember, about 7 centimeters per year, nearly perpendicular subduction in this area. The volcanic arc is being eroded, sending detritus off to the seaward part of the system. There's a long ridge that we will talk about most of the evening or most of the morning your time. This outer arc ridge is formed from highly deformed sediment, stripped off of the oceanic plate, forming a ridge, which then forms a barrier to all the sediment coming off of the volcanic arc to form what we call a four-arc basin. The region of this big outer arc ridge that starts out well below sea level here, eventually comes up above sea level in places like Nias Island and the Andaman Islands, is formed, as I said, of accreted material that came off of the descending oceanic plate. Let's quickly talk about that particular process. How do we outbuild or upbuild that accretionary prism? So we have the Indian Ocean plate being subducted underneath Java. Subduction this way, sediment in the trench is being off-scraped in thrust fault packages and added to the accretionary prism. So this is a zone of material that's been scraped off of the descending Indian plate. It builds this big outer arc ridge. With time, this point here started there a few million years later. More and more sediment is added. More sediment is trapped in the four-arc basin. So the high point of the outer arc ridge migrates seaward. The entire accretionary prism expands with time. In time number 3, it's now well seaward of where it started. It's much thicker, and it has in places a huge concentration of sediment that has come down and filled up the depression behind. All of these symbols here are supposed to represent thrust faults. These are all thrust packages that have been added to the accretionary prism. So let's take a look at some seismic reflection profiles. I hope that people have had some experience at least looking at seismic reflection profiles so you know what I'm talking about. But this first profile I'm going to show you is down here in the eastern part of the region off Java. Remember, subduction here is pretty much perpendicular, not much sediment in the trench. As we look at this seismic reflection profile, this right here is the deepest part of the trench. There's probably about 500 meters to a kilometer of sediment in the trench that is being stripped off. All of this sediment is added in front of this area. Basically, this is a big thrust belt that is continually expanding seaward as more material is being added down at the base, continually being smashed up to form the outer arc ridge or accretionary prism. Accretionary wedge or accretionary prism is all of this deformed material. Here, it's about 40 kilometers from the toe of the trench, toe of the accretionary wedge, up to the top of this outer arc ridge, or in some places called 4-arc high. So we were looking at this part of the system. It gets bigger and shallower, wider as we move up to the northwest. We'll take a look at a seismic profile here in the Sunda Strait area between Sumatra and Java. Here, the thickness of sediment is a bit greater, probably about 1 kilometer or so. Very well-defined zone here where my cursor is right now, that we would call the décollement, where there's separation between this material that's being off-scraped and forms the accretionary prism. This material keeps on going down. Though mostly it's within a couple hundred meters of the top of oceanic crust. In places, there may be small amounts of oceanic sediment being subducted. If we focus in with a better set of processing up here, this piece starts right here, goes over to here. So I'm blowing up this region. You can see much easier now with the color on it. This is the sediment that's being subducted, going down with the oceanic plate. This white zone here is the décollement, where everything above it is deformed. The frontal thrust comes down here, goes all the way down to this décollement, and all of this material is off-scraped to form this accretionary prism or frontal prism. So right now, in this area off between Sumatra and Java, the distance from the toe of the slope, from the trench up to the top of the outer arc ridge is probably about 50 kilometers or so. So it has grown wider and is getting much shallower than it was off to the east. Now, let's take a look at a couple seismic lines that are in or going across the 4-arc basin. So we have accretionary prism here, growing not only wider, but shallower as we go up to the northwest. Sediment is ponding behind. We have one seismic profile here and a second one up in this area. You'll see that they're actually quite different. The first one off Java has, and unfortunately, many of these seismic lines are a few years old, so they're still being shown in two-way travel time rather than depth. But in these areas, you can probably think of one second at 2 kilometers per second probably gives us about 1 kilometer of material. So we have here 1, 2, 3, maybe 4 kilometers of sediment that's filling up this 4-arc basin. sediment in the bottom of the basin. It was a little narrow trough. It had a slope to it. Sediment was onlapping as it filled. That's basin. You can see there's deformation down in here. There's some sort of thrust faulting that's going on along with the accretionary prism, forcing the lower part of the system up into the forearc basin and tilting the strata. So these strata here used to be horizontal all the way. Now they're dipping back towards the center of the basin. So that means there has been compression through here, causing tilting of the forearc basin sediments along this outer arc ridge. Now to the north, the second profile that I'm going to show you has less sediment filling up the trench, or excuse me, filling up the forearc basin. So it's still in the deeper part. There is onlap of sediment filling up the basin. Sediment is coming, in this case, or in this area, off of South Sumatra, coming down, filling up the basin. We still have compression of the outer arc ridge, causing back tilting in this area. Out in front of this and over in here is the main part of the accretionary prism. When we get up further towards Sumatra,